Hey guys, a very good morning. Let me wait 2 more minutes so that we can start with this webinar. Wow, just to join. So let us start with the session. So the topic for today's webinar will be Markov decision process summary, and then which we already covered in our last webinar, and then an eye over the value-based policy methods. So moving forward, if I talk about the topic outline for this today's webinar, the first topic would be the Markov decision process recap from the previous session, and using the example taken in that session. So, determining a drawing line between deterministic and stochastic policies, and then understanding a small grid world problem to understand the state value functions better, and then moving on and understanding action value functions and how to move on gradually to an optimal policy, and then Monte Carlo methods to make a policy better and optimal, and then what is a greedy policy, and how do we can benefit by using a greedy policy, and then the Monte Carlo control methods and temporal difference methods and its control methods. So let's move on step by step to each of our topics. So the first topic, if you remember in the last webinar, we have a example for the Markov decision process. The example was that there is a robotic agent, which the main goal of that agent is to search for as many soda cans as it can while its battery is high. Also, there is a docking station in that room where that agent resides, and whenever the battery is low, the agent should recharge the battery. So, if I talk about, you know, same example, and if we have to solve that problem using two different approaches, being deterministic or stochastic. So, what is the major difference between both the policies and approach towards the solution? So, the major difference is that for a stochastic policy, the, the model already distributes the action and always chooses the probable action, the equivalent probable action from that distribution of actions. Whereas in deterministic policies, usually the action chosen by the agent is based on the reward strategy. So it's very strategic towards the reward. So if I talk about the same example and I say, what's the deterministic policy pi? so that I have a set of states S, which can be achieved by taking set of actions A. So it can be specified as that the agent, if the agent would be low, then it would likely, then it would be recharging its, taking the next action would be recharge its battery. And if the agent is already in a state of highness, then it should search for more soda cans. And similarly, on the other hand, if I talk about the stochastic policy for the same problem, so if the stochastic policy pi for states S and action A, the value lies between 0 and 1. So how we can specify it? So if the what is the probability that if the agent is in a uh, basically agent recharge itself if it's in a low state, so that probability is zero point 0.5. If it's, what is the probability that it will wait, how likely, if its state is low, current state is low, and what is the probability that it will search for a soda can if its current state is low, and what is the probability that it will search if its state is high, and similarly wait if its state is high. So this clearly draws a line between deterministic and stochastic policies. And also in this session, we will, like moving ahead, we will see different kind of algorithms, and then how do we draw a line between deterministic and stochastic policies for those algorithms as well. So let's move on to the next topic for the day. Yeah, so this is a grid world example which will be very helpful in understanding how the algorithm, or how the basically state value function works. So let's constrain ourselves to to this environment wherein the world for this agent is constrained to a grid of 3 by 3. So if you talk about, if you look at the figure, so you can simply see that the agent is sitting at the topmost left corner of this grid to the first grid, and then the goal of the agent is to reach the last grid where the flag is there. So if the agent moves downward, then it will be getting a reward of -1. If it moves again to the rightward, it gets a reward of -1. So basically, the agent will always get a negative reward if it does not reaches its goal, and the negativity, the amount of negativity for that reward varies. So in case of the empty tiles, it will receive a reward of -1, and in case the tile has a mountain, so the reward will be shifted to -3. And in case when the agent reaches to the goal, so the reward will be +5. So if I have to draw a table against this grid world problem, uh, that what is the cumulative reward at at a particular state if a particular action was taken to achieve the goal. So these are the values that I will reach at. So how do we actually calculate them? So it's not the immediate reward, but it's the sum of all the rewards that are that an agent gained during its traversary to the main goal point. So if I look at -6, so whichever paths agent takes, it will receive a -6 rewards. But if the path changes, this reward will also, the cumulative reward will also change. So from here we can see that these values are actually calculated by summing up the rewards that the agent is getting while navigating to the main goal where it has to reach. Now let's move at the next topic, which is linked to this grid world problem. And there is a lot of maths that we bring to the table with the state value function calculation. If I talk about state value function, so it's denoted by V and E for a policy pi. So the value of this, this value function will be the expected value. It's always dependent on the policy that is being taken. So the value of state S under a policy, so it's always influenced by policy. That is a like very essential point that we have to remember here. Is equal to the basically the summing up of all the expected returns for the all the expected returns in timestamp t for all the states that belong to S. So basically, for each state S, it yields some return, and if the agent is in a state S, then as per the policy, it chooses the action for all the next timestamps. So if I move back to the previous grid world problem and see how this calculation is done. So instead of calculating the cumulative reward for each state and action that the agent has taken, what we can do is that the state value function actually follows a recursive property. So basically, you need not to evaluate the values at every timestamp. Rather, what you can do is that value of any state is the immediate reward and the value of state that follows. If I go back to the grid world problem, so if the agent moves from the very first state towards the right, it gets a reward of -1. So this is the value of state is -6, and the reward that it gets is -1. So that amount, and you add it up, that amounts to -5. So that's how you calculate that. And in this case, previous case, the grid value problem and the value table that you see, so that has the discounted factor taken as 1. So if you have as per your policy, you can change that value that should lie between 0 to 1. And then similarly, the as per the different things, the things changes. So value function is the approach to calculate the value function changes from policy to policy. So there is a Bellman expectation equation which calculates the value function differently. How that works is, so it states that in case the policy pi is deterministic in nature, then the agent selects an action where in the set of states of the policy when so it can be written in the form of the Bellman expectation equation. So over the two variables, which are the next state that it will achieve and the reward that it will get. So how do we do that? So basically we have a summation wherein we are summing up the value of all states and the rewards. So basically and also we are taking into account the probability that the agent will reach to a state S naught when it starts from state S and it receives a reward R. And also the value function at the state S naught, it will be additive and it will be like multiplied with the gamma factor, and then you are adding up the return. So basically, this is how your deterministic value would be calculated. And similarly, you can see the equation for stochastic policy. Here, basically, the additional point that you get here in the equation is that the agent selects an action A with the probability pi A when it's in state S. So as I told earlier also, so this stochastic policy, how it works is it models the actions into a distributed fashion, and then using that distribution, it randomly picks up an action rather than actually looking at the reward that the agent will receive to take in particular action. So that's the difference that we can see in the Bellman equation as well. So moving on to the next topic, optimal policy. So basically, it's often possible that you find two different policies which cannot be compared, but they are the optimal against each other. So if I denote the optimal policy by the pi naught, so it will be a condition that the optimal policy would be always greater than or equal to the policy pi. But when that will be possible? When the value function for the states S for pi naught policy would be greater than equal to this for all the states that belong to the set S. So also, we denote the optimal policy by pi star. So it's similarly again the same statement, reiterating over the same thing basically. So the policy pi star would be greater than equal to pi for all the pi that is guaranteed to exist, but it may not be unique. So one optimal policy can be different from the other optimal policy. And the optimal state value function is denoted by V star. Although in this case also, the expected value function that we are going to calculate depends on the policy entirely, but as a matter of fact that it's in the same line, so we denote it by V star. And then we have action value function for a policy pi, which is denoted by uh, Q, and then the Q value that we calculate for a state S and A, and basically it will be again summing up your cumulative rewards for each state and action pair. So how does the action value policy differs from your state value action? It's almost at the similar lines, but herein basically we look at the fact that if I have to convert this action value policy to an optimal policy, then I can basically take the maximum, I can take up the actions which fetches me the maximum rewards to converge to an optimal policy and optimal Q value function. So that's how it differs. Yeah. So let's move on to the next topic. So how Monte Carlo methods are useful, in calculating your Q value or Q table and how they help us. So basically, if your problem statement it involves a greater degree of randomness, then what we should do is we should, like going by the principles of machine learning, we should be collecting a lot of samples of data so as we do not overfit or underfit our model. So that's a very basic thing which Monte Carlo methods also adhere to. And then it implements generally an equiprobable random policy. The name itself suggests that basically it features in the fact that if an agent A is have a set of states S and it takes an action A, so what is the equal likely um, um, you know equal likely probability that an reward R will be attained? So that's how the equiprobable random policy works. So also like Monte Carlo method, using this, you can solve the prediction problems and determine the value function corresponding to a policy. The action value function corresponding to a policy pi in a table is known as Q table. So basically, when you capture the states and actions and rewards in a table for calculating the action value function, so that table is known as Q table and you are calculating the Q value. So each occurrence of the state action pair is an episode. It's called a visit to SNA. So it's like an episodic task. So say for example, if I take the same grid word problem and I say that your agent is a mice which is looking for cheese. So you have small cheese in some of the grids and you have nothing in some of the grids and you have two small cheese and then in one of the grids if the agent will move towards it will die and then there is a big cheese. So, and if take note of every state in action value, basically these are the states. These are the states for that mice, and the actions will be moving towards left, moving towards right, moving up, moving down. And what is the reward that it will attain? So, after agreeing upon that, we can basically fill in this Q table with the rewards that it will receive. And then, for prediction problems and for the estimation of your Q value, so there are two kind of different NC prediction methods that are suggested. So first is first visit, wherein it estimates the Q value as the average of returns following only first visit. Basically, it ignores the later visits and it takes into account only the first visit. And then sometimes, basically, there is another way to do it wherein it estimates as an average of return of all the visits. So it takes into account all the values that you set into your table rather than just the first visit. In alignment to that, you know, we have something known as greedy policies. So, as the name suggests, so a policy can be greedy with respect to an action value function estimate. For if, say, for example, for every state, it is guaranteed to select an action such that that action will fetch the maximum reward. So if you always think about the immediate maximum rewards, it might not be optimal policy, and basically you're exploiting your knowledge. So say for example, there is an agent which has to open two doors A and B, and then it gets a reward on opening those doors. And if on opening one door, it's getting a reward of +5, and so it keeps on always opening that door. So then and it never goes and looks what's the reward behind other door, then that's like an exploitation of knowledge because it's getting a positive reward from behind one door. So that is why it's keep on doing that, so which is like a greedy policy. And yeah, so we have just seen that how finite MDP, how does that it works? Basically, we have an action value function estimate, which is represented in our Q table. And then, to attain the greedy action for each row in table, we need to select only the action that can maximize the row. So that's how greedy policies and actions are selected. But if you want to make a good use of your greedy policy so that they can help you converge to your optimal policy, then there is another variant of greedy policies which is epsilon greedy policies. So a policy is known as epsilon greedy with respect to your action value estimate for every state with a probability of 1 minus epsilon. The agent selects the greedy action. And with a probability of epsilon, the agent selects an action which is uniformly random from the set of available non-greedy and greedy actions. So basically, epsilon greedy policies is, so when you choose an action, you introduce a value epsilon, and using that value of epsilon, you are moving, shifting your choice of your actions towards a random set of actions which are non-greedy as well as greedy. So in this case, you are basically not, exploiting the knowledge, rather you are exploring the environment also. So it's a combination of exploring and exploiting, exploring and exploiting. So that will help the policy to converge to an optimal policy more easily. So let's move on to the next topic. Like as I was saying, so how do the Monte Carlo control methods improve and reach to a optimal policy? So they do an alternating rounds of policy evaluation and improvement to recover to the optimal policy basically. So as we were talking about exploration, so what is exploration in terms of reinforcement learning? Exploration is when the agent draws a balance and it explores and checks for all the rewards, whether they are positive or negative, whether they adds up to the cumulative rewards or they subtracts up from the cumulative rewards. So whatever knowledge they acquire, so they should explore to attain the better judgment. For example, if I take an example of a self-driving car and we use the Monte Carlo method, to train that car to drive safely, and if you just train the car on a straight road and never train it on the turns, so that's lack of exploration for your model building. So that will play a havoc because in this case, our the task is not an episodic one. Rather, it's a continuous task, and also like it's heavy on the budget. So basically, in order so that your Monte Carlo control problems help you converge to an optimal policy. So there is a very fine line which says that you should be greedy in limit with infinite exploration. That you should explore all the options, but you should be greedy also, so that you attain the rewards and learn better actions to take. So the um, every state action pair S and A for all the states that belongs to S and all the actions that belongs to A is visited infinitely many times, and then the policy converges to the policy that is greedy with respect to action value function estimate. Greedy, but it's better. It's greedy in limit with infinite exploration. And then there are some few more concepts which have been introduced by Monte Carlo methods, which will help us converge better and better evaluate our Q table after every episode. So basically, there's a concept of incremental mean that is being done when we evaluate the policy. So we amended the policy evaluation step to update the Q table after every episode of interaction. So after every episode, you take the mean from your Q table, that which is the best action, and you average out the values. And then there is a funda of constant alpha. So you derive that value which uses a constant step size parameter. This would be helpful in a problem, solving a problem where you know your tenure or your time stamp is very important. That you know how much time is there is in between when your agent is in state S1, and then when it moves to state S2 taking an action A1. So that's very, this constant alpha is very helpful there. So it's a step size parameter and it will help you in your learning rate basically. So the value lies between 0 and 1. Higher the value of alpha, faster the learning will be. But the values which are too high, they can, basically prevent the MC control from converging to an optimal policy. How? Because if you know the learning rate is too fast, it might be a possibility that the agent does not learn properly because the learning rate is too fast. Moving on to the next topic. So temporal difference methods. So So this is the major difference between temporal difference methods and Monte Carlo methods is, so the Monte Carlo methods wait till the end of the episode to ask to update the value function estimate, whereas in temporal difference methods, you after every timestamp you keep on updating the value function after every timestamp. So that is why your learning in case of difference methods will be better, and also the performance would be so much better. So TD control can be split into three different kind of um, off policy and on policy control methods that can be used. So first one is SARSA. So SARSA is similar to, like, all of them are basically calculating the Q values, but with a slight difference from each other. So SARSA 0 or SARSA, it's a non-policy TD control method, and to converge to an optimal action value function, so makes uses of the constant alpha that we just spoke about, and the constant alpha should be sufficiently small. And then, if you remember from the epsilon greedy policy, the epsilon value is chosen so as to satisfy the policy greedy in limit with infinite exploration conditions. That means the agent should not be having an exploration or exploitation dilemma, and rather it should be able to, choose the actions such that it's not greedy for the immediate reward, but it's exploring much more options and actions which are from a set of greedy and non-greedy actions. And then we have SARSA Max, or we often call it as Q learning also. It's an off policy control method. So the difference is, it's basically same, but with a slight difference that it, to converge to optimal value, it also makes note of maximum action that would, increase the cumulative return in a way. It also takes into account that. And then you have expected SARSA, which is an on policy TD control method. So in this case, under the same conditions that that will help SARSA and SARSA Max to converge to an optimal policy, it works on the same way. So performance-wise, if we talk about, so the expected SARSA and SARSA, these have a better online performance, whereas the Q learning methods have better offline performance. And of all these, So the expected SARSA is said to be the best one. So, any questions? In case if it comes to your mind that which method is best, Monte Carlo or temporal difference, it's just based on your problem statement that you're solving, the method chosen will be best. So in case, like I just gave an example of self-driving cars, if we choose Monte Carlo method for that, wherein after every episode, like after every crash, in case of self-driving car, you are going to update your q value. So that won't be you know a very good thing to do in case of that problem, self-driving car problem. So instead of that, we should go for temporal difference methods, wherein after every timestamp, after every hit, a very small scratch, you are basically updating your learning curve. So that's the best way to attain it. So and all these methods, they'll probably set up the base for you guys to solve your first project, navigation, which that's a control problem. So yeah, so that will be the end of our session. So thank you for attending it. Thank you.